Something that may or may not have been bothering you since we started talking about these infinite series is the question, if I take an infinite list of numbers and add them up, doesn't that just equal infinity? Isn't this kind of a pointless mental exercise? And the answer is no, it doesn't always equal infinity, which is really weird. A lot of things go haywire when we start thinking about infinity. Now, if we're going to talk about a sequence like the one that we were working on at the beginning of the last video, where we're adding up 3 plus 6 plus 12 plus 24 plus 48. Yeah, this series is going to blow up and become something infinite because we're just tacking on bigger and bigger numbers. But it turns out if the numbers you're tacking on are getting smaller and they're small enough that you might get something finite when you add them up. One example is this series. So if I take 1 and then I add on something half as big each time, so I would add on a half plus a quarter plus an eighth plus a 16th and so on. If I do that, the answer to this infinite series, so literally adding up an infinite list of numbers, the answer here is actually equal to 2, which sounds strange, but I'm hoping to convince you that this is true by showing you a visual illustration. You'll find this GeoGebra applet posted in our resources for the week. And what we're going to do is add up that last series I showed you, the 1 plus a half plus a fourth plus an eighth. We're going to show you that visually. So here I have a rectangle that has an area of 1, and I have the common ratio set up to equal a half. So I'm going to add on something that's half as big. So I'm going to add on a rectangle that's half as big as this one. So I'm going to use this slider. It says slide to have more rectangles. So I'm going to add on this one. This one has an area of a half. It's visually half as big as the first rectangle. So we're going to keep doing this. Now I'm going to add on that 1/4, something that is, again, half as big as the previous one. So that rectangle has an area of 0.25. That has a quarter of the area of the original one. So we're going to keep doing this. Each time I add on a rectangle, it's going to be half as big as the last one I added on. So I'm going to add on another one. That's a size of an eighth, then a 16th. I'm going to turn off these sequences. They're going to get kind of crowded. And as you continue to slide this slider, you're going to see that I could do this for the rest of my life, and I'm never going to grow outside this square that you kind of see outlined on the screen. So I'm going to keep adding rectangles that are half as big, half as big, half as big. This is just, we're going to lose resolution where you can't see it eventually. So this is just going to continue telescoping down into that hole. It's never going to grow outside this green square that we see. And look how big that green square is. The bottom rectangle, remember, had an area of 1, and it looks like we have an exact copy of that on top, another rectangle of area 1, made up of all these smaller and smaller rectangles. So it looks like this series of adding 1 plus a half plus a fourth plus an eighth and so on is going to be bounded by a rectangle of area 2. So hopefully you're getting more comfortable with the idea that you can add up an infinite list of numbers and come up with an answer that is finite. What I want to do for the rest of this section is show you that if it's a geometric series, we have a formula that can actually tell you what that answer is going to be. We'll actually be able to calculate that answer of 2 without having to look at a GeoGebra applet. I promised you a shortcut formula for these infinite geometric series. And to get to that formula, we need to think about partial sums. So remember, our partial sum is the same exact summation notation, just where we stop off at some finite number n. And I'll just copy down our geometric formula, a1r to the k minus 1. And we had a formula for that in the last video that was equal to a1, 1 minus r to the n over 1 minus r. Now, we have to think about partial sums. We are humans. We cannot add up an infinite list of things. So what we're going to do is find a partial sum, a finite sum, and then we'll think about what happens as the number of terms gets bigger and bigger and bigger as we get closer and closer to that infinite sum. So we're going to ask ourselves, what happens when the number of terms that we're taking, is it the 10th partial sum, the 100th partial sum? What happens when this number gets really, really big as it approaches infinity? Well, the only place that that n shows up in the formula is in this term, this r to the n. So we're just going to say as n gets enormous, what happens to that term r to the n? The value of r to the n really depends on what the value of r is. So r to the n, there's 2 things that can happen. So let's imagine that r is 2. So we're raising 2 to the n in that formula. What happens as n gets enormous? So 2 to the 100th, 2 to the 1000th, 2 to the millionth, that's a really big number. Those values are headed towards infinity, just like n is headed towards infinity. So if that's the case, we're going to say that that series is going to diverge. If the numerator of my shortcut formula blows up to infinity, then I'm going to have something infinite. So in this case, we say the series diverges. It's equal to something infinite. On the other hand, if r is tiny, so if it's a decimal or a fraction, turns out it needs to be between -1 and +1. Can't even be equal to -1 or +1. So it has to be some decimal or fraction that's tiny. What happens when you start raising it to big powers, so like 0.5 to the n? You can try it on your calculator. If you raise 0.5 to the 100th or the 1000th, if your calculator has that much memory, then it's going to give you something that's very, very close to 0. These things get so, so small as n gets bigger and bigger and bigger. So in the case that r is small enough, this thing up in the numerator is going to head towards 0. So that only happens if you've got r between -1 and +1. But this is the interesting part of this formula. If that r to the n is headed towards 0 as we head out to infinity, then we can kind of ignore that term in the parentheses of the formula, right? 1 minus something that may as well be 0 is just 1. So this formula, if we head out towards infinity, is going to just have a sub 1 on top and then 1 minus r on bottom. It's important that we always write down that caveat, though, that this formula only works for tiny values of r. So we're going to say if r is between -1 and +1, otherwise the series diverges. You just get a pile of infinity. Okay, so we'll say otherwise the series diverges. So I want to make sure this one works. We kind of convinced ourselves on that GeoGebra applet that if we added up 1 plus a half plus a fourth and so on, we were going to get a finite answer of 2. Let's just make sure that this formula predicts that answer of 2. All right, here's that infinite sum that we're pretty sure is equal to 2, and we just want to make sure our formula is going to tell us that as well. So we had 1 plus a half plus a fourth plus an eighth. This was the one where our common ratio was a half, right? We were cutting each rectangle in half each time. All right, so let's write that in the series notation so it's easier to plug in the formula. So this is going to be the sum k equals 1 to infinity, 1 times our common ratio of a half to the k minus 1. And our formula says that this should be equal to a sub 1 on the top, so 1, and then 1 minus the common ratio on the bottom, 1 minus 1 half. All right, so this one's not too hard to figure out. Let's subtract on the bottom. I've got 1 minus a half is a half, and then we're dividing fractions. So flip the second and multiply. And sure enough, the formula tells us that this infinite geometric series should be equal to 2. I mentioned that r could be negative. It just had to be that small fractional or decimal value between -1 and +1. -1/5 qualifies. This is definitely a geometric looking series. So let's evaluate this infinite series using our formula. So it says we need a sub 1 up top for this formula. That's going to be that 5. And on bottom, we'll have 1 minus our common ratio. And again, it's okay if you go to the calculator, but this one's not too hard, so I'm going to do it by hand. So I've got 5 on top. I'm going to have 1 plus a fifth, and I can just get a common denominator with that 1. We'll make that 5 over 5. So I'll get 5 and then 6 over 5 in the denominator. And then again, dividing fractions, which almost always happens with this formula, you're going to have times 5 over 6. Then just multiplying fractions. We'll remember this is 5 over 1, and we get 25 over 6. Let's try one more. I changed up the index variable for us from k to I. Remember, that's a dummy variable. It doesn't really matter what letter it is. And again, we've got a geometric series. We've got our a sub 1 is 7. Our common ratio is 4/3. So let's evaluate this infinite series with the formula. We have a sub 1 over 1 minus r, which for us is 4/3. And again, this one's pretty easy to do without a calculator. So I got 3/3 minus 4/3. So I get 7 over -1/3. And again, flip the second and multiply -3 over 1. And I get -21 over 1. And that's weird. All right, so think about what this series is. This answer actually doesn't make a whole lot of sense. If I'm adding up these things, remember what this geometric series would look like. This would be 7 plus, then multiply by that common ratio times 4/3. And then we would multiply by another 4/3, and we would keep multiplying by 4/3. These are all positive numbers. How is it that I have added up an infinite list of positive things and somehow gotten negative 21 as the answer? That doesn't make any sense. Infinity is weird, but it's not that weird. All right. The reason why we got this weird answer is because we never should have used that formula in the first place. Remember that formula there at the very bottom, it says if R is in between -1 and +1. And 4/3, that's about 1.333 repeating, that's bigger than 1. So this 4/3 is bigger than 1. If your common ratio is bigger than 1, you should not be plugging into this formula in the first place. I shouldn't have done this. All right. The reason I did do it was to show you that this formula will always give you an answer. If you shouldn't be using it, the answer is going to be nonsense. So you have to check before you start plugging into that formula. It's going to salute you and give you an answer. It's not going to warn you that it shouldn't be used in this case. So because that's bigger than 1, I shouldn't have done anything here. I should have just said this series diverges. So you should have just said this series diverges. And that's your answer. Okay, so just scan those values of R. If it's smaller than 1, then you can plug into the formula. If it's outside that realm, bigger than 1 or more negative than -1, don't plug into the formula, just say the series diverges.